Welcome to The Explainer. Today we're diving into one of the most fascinating and honestly intuitive machine learning algorithms out there, decision trees. What I absolutely love about this topic is how it takes massive, complex data and boils it all down into simple, nested rules that literally anyone can understand. So let's just jump right in.
So, should we play tennis outside today? Think about how your brain actually processes that decision. You don't just guess, right? You ask a sequence of questions. First, is it raining? If yes, you're staying inside. If no, you move to the next question. Is it highly humid? If the humidity is out of control, maybe you skip it. If it's normal, you grab your racket and you go. This step-by-step flowchart logic isn't just how human beings think. It is the exact foundation of a highly powerful AI algorithm.
To really understand how a computer pulls this off, here is our roadmap. We'll look at mimicking human decisions, core tree mechanics, the math of splitting, preventing overgrowth through pruning, the model's strengths and limitations, and we'll finish up with real-world applications. And hey, don't worry if the math sounds a bit intimidating. We're going to walk logically from that basic tennis analogy all the way to high-stakes real-world stuff. Okay, Section 1, mimicking human decisions, from everyday choices to AI. Now, a really crucial point to remember is that a decision tree is a supervised learning algorithm. That simply means it learns by looking at labeled training data. But what's truly amazing here is that this single logic structure handles two completely different types of tasks. On one side, we have classification. This is when the AI predicts specific categories, like deciding if an email is spam or not spam. On the flip side, we have regression. This is where the tree predicts continuous numerical values, like estimating a house price based on its square footage or the number of bedrooms. So, whether it's sorting data into categorical buckets or guessing a highly precise number, the tree uses the exact same flowchart mechanism to get there.
Moving on to Section 2, core tree mechanics, roots, branches, and leaves. Let's look at how this builds structurally.
Picture an upside-down tree. It starts at the top with a root and grows downward. The algorithm uses what we call a greedy top-down approach. Basically, at every single step, it looks for the absolute best immediate choice without worrying about what's coming in the future. Let's walk through it. After you load your training data into that top root node, the AI evaluates candidate splits by testing every single feature, like age or maybe the weather, to see which one best divides the data. From there, it partitions the dataset into smaller child subsets, and then recursively repeats this process for every new branch. Finally, when the tree literally can't split anymore, it assigns predictions to terminal leaves, and that right there is where your final answer lives. Section 3, the math of splitting, finding the perfect branch. So, how does the AI actually know which feature makes the best split? Well, it all comes down to evaluating what we call node purity. We want our data sets to be as cleanly separated as possible. One way the algorithm measures this is through Gini impurity. It's actually the default measure for classification tasks. Now, without getting completely bogged down in the algebra, the equation, 1 minus the sum of squared probabilities, is essentially just a test for disorder. It calculates how mixed up the different target classes are at any given branch. If a node has, say, 50% spam emails and 50% normal emails, it's highly impure. The algorithm desperately wants to find a split that drastically reduces that mixture. Now, an incredibly interesting alternative approach is information gain. Instead of just looking at impurity, this looks at entropy, which is honestly just a fancy word for uncertainty. Information gain is literally the reduction in uncertainty achieved by splitting a node. The math simply finds the difference in entropy between the parent node before the split and the child nodes after the split. The algorithm greedily chooses the split that maximizes this information gain. It wants the biggest drop in uncertainty possible at every single step down that tree. And all of that math, it is chasing one specific number, 0. 0 is the absolute holy grail here. If Gini impurity or entropy reaches 0, it means you have a completely pure node. Every single data point in that leaf belongs to exactly one class. It's 100% pure spam or 100% pure tennis weather. The AI has perfectly isolated the outcome.
Which brings us perfectly to Section 4, preventing overgrowth with pruning, keeping the tree healthy. Because, believe it or not, growing a perfect tree isn't always a good thing.
Here we face the really critical danger of overfitting. If you let a decision tree grow unchecked until every single leaf is pure 0, it's going to memorize everything, including random training noise and weird exceptions that will literally never happen again. It'll work perfectly on your training data, but fail miserably out in the real world. To fix this, we prune the tree. And we have two ways to do it. Pre-pruning means we stop the growth early, setting strict limits before the tree even fully develops. Post-pruning, on the other hand, is the opposite. We let the algorithm grow a massive, incredibly complex tree. And then we go backward, snapping off useless branches that don't actually improve predictive accuracy. Both of these methods balance the model's complexity to make sure it performs well on unseen data. Think of these hyperparameter controls as your mathematical pruning shears. You set these up before running the algorithm. Maximum depth cuts off how many levels deep the tree can go, which saves memory and time. Minimum samples to split tells the tree it needs a certain amount of data to even consider branching out. Minimum samples per leaf prevents the tree from creating a highly specific rule for just 1 or 2 weird data points. By tweaking these settings, you keep your model lean, healthy, and highly accurate.
So, how well does this actually work in practice? Let's cover Section 5, Strengths and Limitations. When to actually plant a decision tree. First up, we have to know how to grade our tree's performance. The evaluation metrics depend entirely on whether we planted the tree to predict categories or numbers. For classification, we look at accuracy, precision, recall, and the F1 score to see how often it sorts things correctly. But for regression, where we're predicting continuous numbers, we use error metrics like mean absolute error or root mean squared error to measure exactly how far off our price or temperature estimates were from reality. So why do data scientists absolutely love decision trees? Well, the biggest reason by far is exceptionally high interpretability. You can literally draw it out on a whiteboard and explain it in plain English to a non-technical stakeholder. Beyond that, it's incredibly flexible. It seamlessly handles raw mixed data, both categories and numbers, without requiring any feature scaling, all while capturing complex, nonlinear relationships that just don't fit into neat straight lines. But of course, we have to look at the limitations. As we discussed earlier, they have a notoriously high tendency to overfit if they're left unconstrained. Because of their greedy top-down approach, they suffer from unstable variance. That basically means tiny changes in your training data can alter the entire tree structure completely. Furthermore, because the rules are strictly greater than or less than, the tree really struggles to draw smooth diagonal decision boundaries, and if your data is heavily imbalanced, the tree will often create biased rules that just naturally favor the dominant class. Let's bring this whole technical journey full circle in Section 6, Real-World Applications, Decision Trees in Action. We started out with a really simple question about tennis weather, but this exact same algorithm is actively shaping high-stakes environments globally. In finance, banks use it for credit approval and risk assessment, evaluating your loan application against strict rule-based thresholds. In healthcare, it powers medical diagnostic flowcharts, helping doctors navigate symptom-based paths to quickly identify illnesses. Businesses use it for customer churn prediction to figure out exactly which behavioral indicators mean you're about to cancel a subscription. And it's running right now in fraud detection, triggering instant security reviews the second a transaction hits a suspicious threshold branch. Which leaves us with one final thought. How much of your daily life is governed by a hidden branch-like AI rule? From the emails getting filtered into your spam folder to the approval on your new credit card, unseen algorithmic branches are analyzing your behaviors every single day, trying to reach that pure, zero impurity leaf. Next time you make a decision, just think about all those unseen decision trees making choices right alongside you. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.